Very good morning, dear students. Welcome back to the subject electrical power generation and economics. In this video lecture, we are going to study about nuclear power plant. Let us have a quick revision of introduction. We all know what is nuclear power plant. Nuclear power plant is actually a power plant in which you have radioactive element as your only fuel. Nuclear fuel is any material that can be consumed that can be consumed that can be consumed to derive nuclear energy, to have nuclear energy. The most common type of nuclear fuel is fissile elements that can be made to undergo fission nuclear fission and your chain reaction in a nuclear reactor. The most common nuclear fuels are uranium-235 and plutonium-239. It is to be noted that not all nuclear fuels are used in fission chain reactions. Other fuels are Neptunium-238, that is NP-238, also uranium-239, also plutonium-241. Now, what is nuclear fission? Let us have this definition. When a neutron strikes an atom of uranium, the uranium splits or divides or splits into two lighter atoms and releases heat. This is our interest, releasing of heat simultaneously. This heat is our concern, primary concern. Fission of heavy elements is an exothermic reaction which can release large amount of energy both as electromagnetic radiations and as kinetic energy of the fragments. Exothermic reactions is a chemical reactions that releases heat, delta H into the surrounding out of the system of chemical composition. What is chain reaction? A chain reaction refers to a process in which neutrons released in fission produce an additional fission in at least one further nucleus, making as a chain. This nucleus in turn produces neutrons and the process is repeated. If the process is controlled, it is useful and it is used for nuclear power. Kindly mark this word. If the process is controlled, we have to make it controllable. A chain reaction is that process in which number of neutrons keep on multiplying rapidly during fission. Up to when? Till all of the fissionable material is disintegrated or broken or disintegrated and heat has been exothermically released into the atmosphere, into the surrounding. This should be in controlled manner. Now, as discussed earlier, chain reaction will continue before every neutron absorbed. At least one fission neutron becomes available for causing fission of another nucleus. And this thing is expressed by multiplication factor. This is expressed by multiplication factor K. If K is equal to number of neutrons, if K is number of neutrons in any particular generation, number of neutrons in the preceding generation. K is your number of neutrons in any particular generation divided by number of neutrons in the preceding generation. If, for example, if the value of K is greater than 1, the chain reaction will continue. The chain reaction will continue. And if value of K is lesser than 1, the chain reaction cannot be maintained. The chain reaction cannot be maintained. Now, what are the requirements of fission reaction? To generate electricity out of radioactive elements, we have to set up nuclear power plant, and we have to go under the process of these chain reactions controllably. We have to control how it is being controlled. We'll see this later on, but just have a quick look on the requirements of fission process. The neutrons emitted in fission should have adequate energy to cause fission of another nuclei. The produced number of neutrons must be able not only to sustain this fission process, but should be able to increase the rate of fission. This process must be followed by liberation of energy. What is liberation of energy? Liberation of energy means heat content must be your end product. It must be able to control the rate of fission by some means. It should not be uncontrollable. It should be controllable. Control the rate of fission. Critical mass. What is critical mass? The minimum quantity of fuel required for any specific reactor system is called critical mass, and size associated with it is called critical size. See this. This is your first generation, as it is written here. This is first generation. It goes like this, bombarding this, producing one or two nucleus. This is bombarding another one, producing another set of third and fourth. This is bombarding another set, producing another set of 5 and 6. This is producing 7th or 8th. This is 9th or 10th. This is 11th or 12th. This is 13th and 14th, and it goes like so. This is the results given. This is neutron. This is uranium-235 atom. This is showing you how chain reaction is increasing generation by generation. The number of neutrons evolved out of one bombarding of one neutron into the uranium-235 atom, increasing the number of neutrons released and also the release of heat. This process must have released heat. release of heat, release of heat, release of heat, release of heat. Okay, at every step, at every generation, there is a release of heat, liberation of energy. And this is our primary concern, this liberation of energy. This is the heat we are actually using to make steam. When the steam is made out of this heat energy, out of this liberated energy, the process of generation, the process of making power, or the process of generation of electricity or power is the same as we have seen in your thermal power plant. This is uranium 235 plus neutron bombarding. This is the bombarding. Fission reaction is happening, plus 2 or 3 neutrons, generally 2 or 3 neutrons are evolving, plus this is a 200 mega electron volt. This is your energy evolved into the system. Mega electron volt, mega electron volt. Each electron, if each neutron releases 2 more neutrons, then the number of fissions doubles each generation. We have seen in the previous slide. This is the schematic diagram of nuclear power plant. See this. This is nuclear reactor in a safe housing. This is controlling rods. This is controlling rods. What is happening inside this nuclear reactor? This is uranium 235 bombarding plus neutron, releasing 2 neutrons or 1 more neutrons plus delta H. That heat energy, that delta H energy is actually taken out with the help of this coolant. This is your coolant going into this furnace. This has a separate arrangement. This coolant is absorbing this delta H and coming like this, heat tapped, and this is going into this. The heat content is coming out like this. See this, and it is heating the water in the process of making steam. This is the generation of steam here. This is the generation of steam here. Superheated steam, once it is superheated steam, it is coming out of this arrangement. This is your prime mover. This is your prime mover. What is the prime mover here? Obviously it is turbine. This heat is coming, and depending upon the nature of its delta heat, delta H or pressure, this starts revolving, rotating. This is the common shaft on which it is mounted. This is the common shaft on which the prime mover and the turbine is being mounted, and this is a generator, which generator, synchronous generator, made to generate electricity, RYV. Step up, then After stepping up this generated voltage, it is transmitted. This is the detailed schematic diagram of nuclear power generation with all the labeling. As we have seen in the previous slide, this is a control rods which is controlling the chain reactions. It must not go beyond your control point. It must not be uncontrollable. Otherwise, it will become a fatal. This is your fuel rods. This is your fuel rods. This whole thing is called nuclear pressure vessel. This is nuclear reactor. This is pump, pumping water from this position to this. This is coolant water. Now, hot water is coming like this. This is steam, high pressure. High pressure and high temperature here. The steam entering with high pressure and high temperature here, and thus it makes this turbine movable. RPM increases as pressure and temperature both is high at the input level of turbine. This is mounted on the same shaft. This is a generator, and electric power is the output. This is your steam generator. This is again your pump coming from pumping water from low pressure to high pressure. This is coolant in. This is coolant out. This is steam condenser. We have also studied condenser or steam condenser in our previous video lectures. This is actually the exhaust gases collected here. Gases means steam here, collected here, and this is fed back into the system, that is water from low pressure to high pressure. Steam entering at low pressure. Now, this whole arrangement is called this one. This whole arrangement is called primary loop. Primary loop contains reactor vessel, reactor pressure vessel, pump, reactor, control rods, arrangement, fuel rods. This is primary loop 1. Now the another one is your secondary loop 2. That is it contains steam generator, turbine, steam condenser, prime mover, steam condenser, and all these explanations in front of you. Nuclear reactor gives you a green energy. The pollutions during the production of energy, during the production of power, there is no smoke here, as we have in coal-based power plant, thermal power plant. There is no burning of coal here, so it is green. It is green power. The capital cost is higher as compared to other one. Capital cost is higher as compared to your thermal power plant because much of the investment is made into this reactor. This reactor is actually a challenge for the developer of this nuclear power plant to develop a very safe and very long lasting reactor, and to ensure any leakage must not be into the atmosphere. If there is leakage, radioactive leakage, this is not favorable for the whole ecosystem. It should be avoided. So a heavy amount of money is invested to lay out to make the infrastructure of this reactor, this primary loop. Once the steam, you can observe this, once the steam is generated, once the steam is coming into the picture, the whole process after this steam is same. What is this whole process? The whole process is turbine and generator. This is the whole process, which is common to your thermal based power plant, coal based power plant, thermal power plant. This is all about this video. I'll be coming with more topics of this subject, this unit. Till then, thank you so much. Thank you for watching.